All right, hello everybody. Welcome back to the second mini. So the second mini is going to be very much like the first mini. We had a slight problem with Canvas. I posted about it on Piazza. I think it should be fixed now. It looks like we certainly have a lot of people in the roster on Canvas. So if you haven't already done so, you should check out the Canvas site. It's got our syllabus for the mini on it. I don't want to spend a lot of time going over the administration. I guess the main things to say are that the grading is going to be very similar to the first mini. So if you were part of the first mini, then you shouldn't be surprised. And if you're new this mini, have a look at the syllabus. It's available on Canvas, and it'll tell you everything you need to know about grading, what types of technology we're using, all of that sort of stuff. Let's instead just jump right into the content for the new mini. So whereas the first mini was almost all about mathematical techniques that, you could see that they were useful in general, but we didn't actually do more than a few simple examples of how they would get used in machine learning. The second mini is going to be more about techniques that are more obviously machine learning related. So things like how to use probability distributions to model the world. So we're going to depend heavily on the stuff that we learned in the first mini. So if you're new here for the second mini, welcome, and have a look at the first mini's syllabus, which is available on Piazza. That syllabus post is going to become a good friend because it gives you links back to all of the lecture notes for all of the topics that we discussed, in case you need to review them. So let's get started with one more technique, which is information theory. So these notes are linked from the syllabus post for the second mini on Piazza. So both the first and the second mini are pinned to the top of everybody's feed. So let's start talking about information. So suppose we have a random variable, let's call it x. And it takes values, it's a discrete random variable, so it takes values in the set 1 through k. And let's suppose that there are two people who we'll call, through long tradition, Alice and Bob. And Alice and Bob both know the distribution of x, they know p of x, but only Alice knows the actual value of x. So Alice obviously knows more than Bob does, but how much more information does she have? Well, we could consider having Alice tell Bob the value of x. So for example, she could send an integer from 1 through k in the standard ceiling of log k bit representation. And so if Alice can do this, if Alice can tell Bob the value of x using at most b bits, then we say that Alice has b bits more information than Bob does. Now, this might or might not be the best code to use, right? So a code is an assignment of bit strings to the different possible values of x. And so sort of this, let's say we have 4 possible values. The standard code that you would use if you didn't know anything more would be 0, 0, right? The 2-bit string, both of which are zeros, would correspond to the first value of x. 0, 1 would correspond to the second, and so forth, up through all 4 possible values of a 2-bit string. And so that gives us an upper bound to start out with, right? If there are at most 4 possible values, then there's at most 2 bits of information in them. And in general, if there are at most k values, then there's the standard code for integers gives you the ceiling of log 2 of k possible strings, and that's what you use. All right, So just a quick digression into information transfer, into direction of transfer. So it's going to be important to pay attention to which direction the messages are going, right? So the sign that we've chosen is that information from Alice to Bob counts as positive information. And so if instead Bob had extra information compared to Alice, we would call that negative, just to keep consistent. That would mean that there were messages going from Bob to Alice. But let's stick with Alice having the extra information and Alice sending a message to Bob. All right, so how well can Alice do? Right? So if the distribution over X is uniform, it turns out that the best Alice can do is to use the standard representation of the numbers from 1 to k and just send a bit string to Bob. But suppose that, so here's the uniform distribution over 4 outcomes. Suppose that instead the distribution were this one over here on the right. So half of the time you get the first outcome, a quarter the second, and an eighth for either of the other two. So you might think intuitively that in the distribution on the right, there's less information that Alice has to tell Bob, because Bob has a pretty good idea, even before hearing any message from Alice, that it's most likely to be the first outcome. So if we want to take advantage of this, what we can do is have Alice assign shorter code words to more probable values of our random variable. And then if that's true, if she does that, on average she's going to send fewer bits, right? Because most of the time it'll be a probable value, and then she'll send a short message. And so in this case, instead of having a message of a constant length, the length of the message actually is random. It depends on which value of X Alice observes. And so we're going to measure information by the expected length of the message. So, for example, let's say that the distribution is this one here, and let's say Alice picks the code words here for the 4 possible values of X. So on average, she's going to send, well, so half of the time it'll be the first outcome, and she'll send a 1-bit message, just the single bit 0. A quarter of the time, she'll send a 2-bit message. And then an eighth of the time, she'll send this guy, and another eighth, it'll be that guy. And so for each of those cases, it'll be a 3-bit message. And if you work that out, that averages out to 1.75 bits on average, which is strictly smaller than the 2 bits that she would have sent if she used the standard code. It turns out that this value is optimal for this distribution. There's no code that uses fewer than 1 3/4 bits per sample of X in expectation. All right, so just a subtlety that is worth talking about. If we take a look at this code, it satisfies what's called the prefix property. For each of these code words, let's say this one, 0, it's not a prefix of any of the other code words. So no one of these other code words starts with 0. Or for this one, right, 1, 0, there's no other code word that starts with 1, 0. That property is important because it means that Bob knows when Alice is done sending the message, right? Because, as soon as she's sent bits that form a complete message, then there's no other message that she could be trying to send. And so, so then Bob knows she's done. If this were not true, then there would have to be some other mechanism for letting Bob know when the message was over. Maybe there would be like a third symbol that you send along the line, or maybe there's another line that you send a bit along whenever the message is done, or something like that. And the point is, this other channel would be carrying some information, and we'd have to count it too. So in order to make sure that we're using just the one channel, just the one message that Alice is sending Bob, we force the code that Alice is using to satisfy this prefix property, because otherwise there's some way, there's got to be some external mechanism, and we'd have to figure out how to count the information in that external mechanism in the total information that Alice is sending. All right, so suppose that we have this code and we know that Alice uses b bits on average to tell Bob about the value of x. B is an upper bound, right? We know Alice has at most b bits more information, but we don't know that she's doing as well as possible because some other code could be better. So it's nice that there is, in fact, a lower bound that we can use. We aren't going to prove it, but if we have some distribution p over x, then there's no code that can use fewer than h of p, which is called the entropy of p, bits. And that value is defined to be the sum over all possible outcomes of minus p log p, right? The probability of that outcome times the log base 2 of the probability of that outcome. And this value is called entropy of p, and we'll also sometimes write the entropy of x, so the entropy of the random variable, even though strictly speaking it's the entropy of the distribution of that random variable. So if we calculate the entropy of that distribution we were using before, here it is, we get 1.75 bits, and this is how we know that the code that we were using is optimal. We have a code that uses 1.75 bits on average, and we know that no code can use less than that, so we must be optimal. Oh, I should say, by the way, for anybody who's new, please join us on Piazza and ask any questions that aren't clear during lecture, and I'll try and answer any of them that I see in lecture stream. Looks like no questions so far on Piazza. Hopefully that means everything is clear, but go ahead and ask questions and we'll cover them if we see them. All right, so this lower bound turns out to be tight. There are, no code can be better than that, and it turns out that you can get that value exactly. Or more precisely, if you're doing it a whole bunch of times, then per sample from this distribution, you won't need more than the entropy number of bits on average. And so there's one code that does this is called the arithmetic code. We won't go into how to construct it, but if you're interested, you can look it up. So because of this, we can think of entropy as a measure of information, right? By knowing x, Alice has, on average, h of x bits more information than Bob does. Entropy is also a measure of certainty, or I guess more precisely, uncertainty. It's the number of bits worth of uncertainty he has, or the number of bits he needs to become certain. So I mentioned that the bound is only tight in the long run if you're sending lots of messages. For a single sample, you might need more than h of x bits because of the fact that messages have to contain an integer number of bits. So if you want to see the problem, imagine that there's an outcome that has probability 1/3. How many bits should you assign to that outcome, right? You'd like to assign log 2 of 1/3, but that's not an even number of bits. In fact, it's not even rational. And so what you have to do is use a method that on average assigns that many bits to that outcome. All right. So just to get a little bit more intuition about entropy, the distribution with the most entropy is the uniform distribution, and that has an entropy equal to the log base 2 of the number of possible outcomes. The distributions with the lowest entropy are the ones that are certain. In other words, they place all their probability on a single outcome. They have an entropy of 0 bits because Alice doesn't need to send a message to Bob at all. Bob already knows the value of x. And so distributions that have higher entropy, we think of them as closer to uniform, and distributions that have lower entropy, we think of them as closer to being certain. when we're evaluating the expression for entropy here, we need to have a convention for what 0 log 0 is. And we do that by the limit as p goes to 0 of p log p, which turns out to be 0. Yeah, okay. So we could, of course, use a code that isn't binary, right? We could use a code with 3 or 5 or 17 different possible symbols, or 26, right? And in that case, it would make sense to measure entropy in base A if there are A symbols instead of base 2. So it's a perfectly good way of defining entropy as well. You can define it as P log base A of P summed over all possible outcomes. And it turns out that this causes a difference that's only a scaling factor. So we're essentially using a different unit of measurement. We're using symbols base A instead of bits, which are base 2. We can even, in fact, extend this convention to use a non-integer base. Not really clear what that means physically, but effectively, you just convert into an integer number of symbols in your code in order to send your messages, and you take account of the scaling factor. If you use base E, the unit is called a nat as opposed to a bit. And again, you can't actually send messages in nats, right? You have to convert to bits or something else to send them, but a lot of times it's convenient to use nats because the natural logarithm has some nice properties. All right. Suppose instead that Alice has, oh, here we go. We started to get a bunch of questions. Okay, so somebody wants to know how we chose the code. Going back up here, right, this code right here. So I guess I chose it by inspection. But there's a couple of methods that you can use to choose it automatically. One of them is called Huffman coding, which I think will get essentially this answer. And then arithmetic coding is a little bit more sophisticated. Basically, it handles probabilities that are not powers of 2. And it's even more complicated, but it's deterministic and it's extremely widely implemented. And so, I would expect the Wikipedia article on arithmetic coding to be good. Why is the log not used in the calculation of the entropy of the example? So I assume that means this example. And in fact, what's happening is, right, okay, so that's actually a really good observation, right? So we picked this code so that the length of each code word is equal to the negative log of the probability of the corresponding outcome, right? So here, the negative log of a half is 1, and so we picked a 1-bit code. Negative log of a quarter is 2, and so we picked a 2-bit code, right? And then 3-bit codes for each of the eighths. And so the log is in fact used here. It's just hidden by the fact that we picked an optimal code, which requires us to pick code words that are the log of the negative log of the probability. Right, and so somebody's asking actually exactly that. Should we use log 2 of the probability of an outcome when assigning a message to a given outcome? Yes, except that that might not be an integer, and so you have to be fancier in that case. And arithmetic coding is how you be fancier. Why is the entropy negative? The entropy is positive, right, given this definition, unless I've missed a sign, right, because log 2 of p is less than 0 and we put a minus sign, right, because p is less than 1. So yeah, so this definition of entropy is always positive. And it's the reason, I mean, it's an arbitrary convention. Typically, people call it entropy for the one that's always positive, and negentropy for the one that's always negative. But you could flip it, right? Negentropy is a perfectly useful function as well. And again, it's a convention that positive entropy means a message that Alice has to send to Bob. So we chose a sign arbitrarily, and everything will be good as long as we stick with our convention. All right, so good questions. Let us continue. All right, joint entropy. So suppose instead of just one random variable, x, Alice knows two random variables, x and y. And Alice and Bob both know the joint distribution of x and y, and Alice knows the actual values, but Bob doesn't. So how much more information does Alice have than Bob? It turns out this is actually a special case of what we've done before. If we define a new random variable z, which is equal to the tuple whose elements are x and y, then z is a random variable, it has a distribution, there's an entropy for that distribution, and Alice has that many more bits than Bob does on average. And so h of xy is just defined to be the entropy of this joint random variable, the tuple of x and y. And there's an explicit formula for it, which is this right here. You just sum over all possible values of both x and y, the joint probability of x and y times the log of that joint probability negated. But now, given that we've split up into two random variables, we could have Alice tell Bob just one of the random variables at a time. So if Alice tells Bob y first, then she has to use on average h of y bits. And now Bob knows y and not x. And now the question is, how much extra information does Alice still have, right? So before she had h of xy bits, and now she sent Bob h of y bits, and so she has the difference left, right? Because it turns out that if you want to tell Bob both x and y, it makes sense to, it's optimal to tell him first y, and then to tell him x, given that he already knows the value of y. So this value here, h of xy minus h of y, is called the conditional entropy of x given y. And we can actually manipulate that in an interesting way. So here's the expression that we had before. Definition of the joint entropy, and the definition of the entropy of y, right? The minus sign cancels, so you have a plus. And now we can use the sum rule, right? For any possible value of y, we have that p of y is the sum over x of p of xy. So that means that p of y is, you can just have a sum over x p of xy there. And that means that you can combine these two terms, right? You have sum over x, sum over y, p of xy, log 2 p of xy, and then because this term has the opposite sign, minus log p of y, which is the same as log of p of xy over p of y. And then this here is the conditional probability of x given y. So that's called, so then we get that the conditional entropy is the sum over the joint distribution of the log of the conditional probability, right? So that's a very useful expression for the conditional entropy. Let's see. So we can also write, instead of conditioning on y, like taking the average over, or instead of looking at this conditional entropy, right, we can condition on a specific value of y, right? So we can write the entropy of the conditional distribution of x given a specific value of y. This is just the entropy of that conditional distribution. And by looking at this up here, right, we can factor p of xy as p of x given y times p of y. That's the chain rule of probability. And then factor out p of y. So then this expression up here tells us that h of x given y is just the expectation over all possible values of y of the entropy of that conditional distribution, right? So this kind of makes sense. The conditional entropy is the expectation of, over all possible values of x and y, of the number of extra bits Alice needs to send Bob to tell him X after Bob already knows Y. All right. So I think I just said this, but the conditional entropy measures how much information is left in X after we figure out the value of Y. So in particular, if X is a deterministic function of Y, then h of X given Y is 0. And if they're independent, then h of X given Y is just going to be h of X. Knowing Y doesn't help Alice send an informative message about X. All right. So just like there's a chain rule for probability, there's a chain rule for entropy. The joint entropy is the sum of the entropy of one variable plus the conditional entropy of the other variable given the first variable. This is just a rearrangement of one of the equations we showed earlier. But you can also do it for more than two variables by induction. So we have h of x1 through xk is h of x1 plus h of x2 given x1 plus h of 3 given x2 and x1 and so forth up to h of xk given all of the previous ones. Another useful identity is that the joint entropy is always less than or equal to the sum of the individual marginal entropies. And that makes sense because on the right, what we're saying is we're sending, Alice is sending Bob a message about X and then separately sending a message about Y without paying attention to the fact that Bob knows X. Whereas here, h of xy, Alice can send X and then send Y conditional on X, which might be a shorter message if X gives you some information about Y. And this equality, this inequality, as you might expect, is an equality if and only if X and Y are statistically independent. All right. Somebody's asking, what is arithmetic coding? I don't think we have time to go over in detail in this class, but it's an algorithm for constructing a code that achieves, on average, the minimum possible bit length given a particular distribution over a variable. So you can think of it as doing its best on average to assign code words whose length is equal to the negative log of the probability of each outcome. And it's a way for the first time you transmit a symbol, you might use one code. The next time you transmit it, you might use a different code. And on average, over all the times you transmit that same outcome, that same symbol, the length of the code averages out to minus log 2 of the probability of that outcome. All right. So far we've assumed that Alice and Bob know the distribution of X. And we're going to continue to assume that Alice and Bob agree on the distribution of X, but let's suppose that they are wrong, that X actually follows a different distribution. How many bits are they going to use, right? Well, so Alice could be, let's say the true distribution is Q. Sorry, they think the distribution is Q and the true distribution is P. So because they think the distribution is Q, they'll pick a code based on Q, which has on average log 2 of Q of X bits to transmit the value X. But the actual distribution is P, so when we take expectations, we have to use P instead of Q. So that means that the expected cost is the sum over all outcomes of the probability of that outcome times the length of the code, which is minus log 2 Q bits. Sorry, this should be negated here. I'll fix that. So as you might expect, the cost when they're using the wrong distribution is always at least as high as when they're using the right distribution. And the difference in costs, the extra cost, is called the relative entropy, or the KL divergence between the two distributions. So just writing that out, it's the sum over all distributions of the expected cost using the incorrect distribution minus the expected cost using the true distribution. And because using the wrong distribution is never optimal, this is always going to be non-negative. And as before, we've written the distribution, written the definition in terms of bits, but you could use any other unit like nats if you wanted to. You could use base 17, base 256, right? Whatever you prefer. For KL divergence or relative entropy, people actually typically use nats, but you'll see all of the versions fairly frequently. So from the name, you might think that relative entropy generalizes regular entropy, and in fact, that's true. If you take Q to be uniform, right? If you say that Alice and Bob think that the random variable is uniform, then the KL of P and Q is going to be exactly the it's going to be the entropy plus a constant, because log 2 of Q is in fact going to be constant. Somebody's asking, why is the cost always no lower than the cost of an optimal code? That's the definition of optimality, right? So the optimal code is in fact the shortest, and so if you choose a code based on an incorrect assumption, you might choose a different code, which will then potentially not be optimal, and so you can't do better than optimal, because that's what it means to be optimal, but you might do worse. All right, so relative entropy is asymmetric. The entropy between P and Q is not in general equal to the entropy between Q and P. It's kind of hard to visualize exactly the way in which it's asymmetric, but sort of a brief intuition, a brief intuitive description is that KL divergence is large if the true distribution P places high probability on outcomes that the incorrect distribution Q considers unlikely. Right, so that means that if you think that a particular symbol is really unlikely, right, then you're going to assign it a really long code. And if it turns out to be frequent, then you're going to be paying the length of that code really often, and so you'll be really unhappy. On the other hand, if you if it's the other way around, if your false distribution Q places high probability on an outcome that truly doesn't actually happen, well, you'll assign a short code to that outcome, which is going to be wasteful because you couldn't use it for some other outcome, but you're not necessarily going to be really hurt because there are other short codes that you'll assign to the other likely outcomes. All right. So over time, we might see a whole string of random variables that are dependent on one another. A good example of this would be inference of a parameter from data, right? We described that a few times during the last mini. So we're going to start off with a prior distribution over our parameter, and we're going to try and learn about that parameter from data. So here we're playing the role of Bob. We're missing some information. What's the true value of the parameter? And nature is playing the role of Alice. Nature is telling us stuff that lets us figure out about theta. Nature may not be using an optimal code, but it still helps to think about information in this case. And so over time, we see a sequence of observation, and our distribution starts off as our prior P of theta, then it becomes P of theta given x1, and P of theta given x1 and x2, and so forth. And each one of these examples changes the amount of information we have about theta. And so the entropy of the distribution also changes, right? It's in expectation, h of theta given x1, and so forth. At the beginning, we're going to have high entropy because we don't have much information. And as we see more information over time, our entropy is going to go down, right? We're going to, on average, get more information every time we get a message, because we can't lose information in expectation by seeing a message. Now, this decrease is not like it's not always going, so in expectation it's always going down, but for any specific sequence of observations, it might sometimes go up and sometimes go down. And basically what winds up happening is that sometimes if we see a really surprising value of xi, that's going to mess with our mess with our mind. It's going to cause us to become confused because we thought that this shouldn't happen and it actually did happen. And so in a case like that, the entropy can actually go up. But because that only happens when we see really unlikely values of the observation, it doesn't happen that often, and on average our entropy keeps decreasing. Oh, yeah, so a conceptual question. Somebody's asking, how can we know P of X if we don't know P? So I think there's sort of two situations here. One situation is that we're thinking of this as a thought experiment, right? We don't know P, but we're going to suppose that Alice and Bob do know it, right? And then it's still useful as a thought experiment to say that, suppose Alice and Bob did know this distribution, what would be the length of this optimal code to send the information between the two of them, right? The other possibility is we might actually know P, right? In many circumstances when we want to calculate h of P, we know the distribution, and we can actually go and do the sum to calculate the entropy. So those are the two possibilities. We don't have to know P in order to talk about its entropy. If we do know P, then we can actually compute the entropy. And if we don't know P, then we can reason about the entropy in the abstract, but we won't be able to compute a numerical value for it. All right. So I think that's the end of this set of lecture notes. Again, keep the questions coming. They've been really nice. And while we do that, I'm going to start the next set of lecture notes. I suspect we won't finish before the end of class, but we might as well get started. All right. So I promised that we would talk about solving machine learning problems, and we're going to start by talking about an incredibly simple and maybe too simple problem, but we'll get more complicated later, I promise. So whatever problem we're going to solve, a lot of times the first step is to set up a model, meaning we're going to list out the random variables that we're interested in. Maybe it's a parameter vector, maybe it's some data that we might observe, that sort of thing. And then we'll have some kind of a structure that describes how they relate to one another. So often that structure is a joint probability distribution for all of these random variables. Sometimes it's something else. But for now, let's suppose it's just a joint probability distribution. And in particular, what we're going to do is, if we know the model perfectly, if we already know the joint distribution of everything, then there's not much more that we need to do. But instead, what we're going to do is we'll say that there's some model class, meaning that there's a parameter vector, let's call it theta, and we don't know theta, but for each possible value of theta, there's a model that describes the world. And our job is to figure out what is the value of theta that best describes the world. And then when we do that, we can use methods like maximum likelihood, which we covered at the end of the first mini, to try and figure out the value of theta. And so in order to use maximum likelihood, we have to figure out how to make this model. So let's start talking about how do we make models. And we're going to start by making a model for just one discrete variable. Again, this is maybe too simple to be interesting in practice, but you have to start somewhere. And later we're going to talk about continuous variables and how to generalize to multiple random variables. So if we have a discrete random variable, there's a bunch of distributions that we could choose for it. We already saw in the example of a coin flip the use of a Bernoulli distribution as a model. A few more distributions that you'll see often when modeling discrete variables are categorical, multinomial, Poisson, and maximum entropy. And in this set of lecture notes, we're going to describe each one of those in turn and give a bit of intuition about each one. All right, so the simplest case is categorical. The random variable takes one of k different values, and we specify the distribution by just listing out a probability for each one of these values. So we already saw Bernoulli for a coin flip. The two values are heads and tails, and we list out probability of heads is, let's say, 70% and tails is 30%. We could also have a die roll or something more complicated, like let's say you get a newspaper, take the front page, randomly like throw a dart at the front page, and whichever word you hit, count the number of characters in that word, and that's the random variable, right? And so there's, you could have anything from, just 2 outcomes up to thousands, millions, billions of possible outcomes. If there are k possible outcomes, we have k minus 1 degrees of freedom when we're choosing a categorical distribution. Right, there are k probabilities, but we lose 1 degree of freedom from the constraint that all of the probabilities have to sum to 1. All right. A multinomial distribution is the next one to look at. So let's say we have a categorical distribution, and we sample from it n times, and we count the number of repetitions of each outcome. So we have a pair of dice, we roll them n times, and we have a distribution over the total number of spots we observe, for example. Right? And so, for example, 7 is going to be more frequent than 2, and so on average, the number of replications, the number of duplicates of 7 is going to be higher than the number of duplicates of 2. And so a sample from a multinomial distribution is just a vector of counts, 1 count for every outcome. So our biased coin example, we could get the vector 17, 3, meaning 17 heads and 3 tails. If we have if our random variable is words, we would get a vector of counts, 1 for each possible word in our vocabulary. So that could be a very long vector. If there's only 2, it's called a binomial distribution. More than 2 is called multinomial. A single sample from a multinomial we can display as what's called a histogram. So here's an example of a histogram. It corresponds to the following experiment. We choose 123 different US states uniformly with replacement and count how many characters are in the name of each one. And so the outcome of that experiment is a multinomial random variable. N is 123, the number of samples we took, and the probabilities for each outcome are determined by the table of state name lengths. And so I actually ran this experiment, and I got this sample from the multinomial distribution. And you can see, for example, that about a quarter of the states that we sampled had 8 letters in their name. I don't actually remember what the list of 12 states that have 8 letters in their name is, but at least if you go by the table that that I downloaded off the web, that is that's the true number. All right, so again, I want to emphasize that this histogram represents a single sample from the distribution, right? So a sample from a categorical distribution is 1 outcome, and a sample from a multinomial distribution is a histogram of many possible outcomes of the original categorical. Let's see. Oh, and here's an expression for the probability of a given sample. We're not going to derive it, but you can think basically that each one of these terms, like p2 to the x2, gives us the probability of getting x2 copies of the second outcome that has probability p2. And then because we ignore the ordering, there's a constant that doesn't, basically a constant to correct for the fact that there's many possible orderings that correspond to each sample, and a different number of orderings that correspond to different samples. All right, so Poisson, the next distribution is Poisson. So a sample from a multinomial distribution is a vector of counts, right? How often did each particular event happen over the course of a fixed number of trials? So counts are a good source of discrete random variables, but there's another common situation for counts, which is instead of fixing the number of trials, what we do is we say that we fix the total amount of time we're going to observe and watch for events that happen at some given average rate. So you imagine, for example, we stand at an intersection and watch how many purple cars drive by, right? That's something where presumably each individual purple car is an independent event, and it has some low-ish probability, and we can count how many purple cars drive by in, let's say, an hour. So that gives us a Poisson random variable. Maybe some more common situations where you would use one is, let's say you're running a restaurant and you want to know how many separate parties of customers are going to arrive between noon and 1. That could be a Poisson distribution. Or let's say you're building a camera with an image sensor and you want to know what's the distribution of the number of photons that hit a particular pixel in your image sensor over a few milliseconds. That actually like for your cell phone camera, that doesn't matter so much, but for something like a camera attached to a telescope, right? Single photons turn out to be actually quite important, and you're watching such a dim source that you expect counts in the single digits perhaps of the number of photons that you're going to get. All right, so again, we aren't going to derive this expression, but somebody has gone ahead and derived for us that the probability of observing X events under a Poisson distribution is this expression, where it has one parameter lambda, which is called the rate. Lambda tells us how many events we expect to see on average during our observation period, right? So here's a graph of for each possible number of events, what is the probability of seeing that number of events when the parameter is lambda equals 7? And so you can see that, here 7 is one of the most likely outcomes. All right. So it's good to, so almost always when you're counting events, one of those two situations hold, that you're going to go through a fixed number of trials where one event can happen per trial, and that gives you a multinomial distribution, or you're going to observe for a fixed amount of time, and events are just going to happen at random during that interval, and you count how many of them you see. There are other possible situations, but those are the two most common. And it's good to be able to match those to the two distributions, a Poisson and a multinomial, so that you know which to use for modeling. All right, so now we get to a much larger family, right? So I should preface this by saying there's a gazillion different possible distributions that you could assume for your discrete random variable. The ones that we've described so far are three of the most common. They come up just all the time in modeling. If you need more examples of ones that people have worked out in excruciating detail, every probability textbook will, or just about every probability textbook, will have in the back a list of common distributions, and there'll be, a dozen or 2 dozen, depending on, how many pages in the probability textbook. There'll be a dozen or 2 dozen examples that, each cover some fairly common situation. What I'm going to talk about now is a recipe for deriving a discrete distribution for a new situation. And as such, it's going to take a little bit longer to describe, but it's going to give a whole lot more options. All right, so a very general way to describe a discrete distribution is through numeric features of the possible outcomes. So if the outcomes are integers, we could use x and x squared as our features, or x squared, x cubed, right? Or if the outcomes are US states, we could use their populations and the number of characters in their name. Or, I mean, you can come up with, if they're people, right, you could use their, their heights and whether they like the movie Amelie as features, right? You can come up with as many different feature vectors as there are situations. And so this feature function, right, it maps an outcome to a vector of numerical features. That has essentially the same purpose as the feature function that we used last mini for doing classifiers like the perceptron or the Fisher discriminant. And the purpose is basically, instead of working directly with the outcomes, because that might be a pain to model directly, we're going to work with a possibly nonlinear function of these outcomes, which might be easier to model. All right, so we fix a set of outcomes and we fix a list of features, and we can describe our probability distribution by saying what's the expected value of each one of these features. This is not necessarily a complete description, but it's some useful information. And to give an example, here are 2 different distributions over the numbers 1 through 10, right? So one of them is uniform. Q is uniform. It gives the same probability to every integer. This one is not uniform. It gives smaller probability to smaller integers and larger probability to larger integers. And so if you take the features x and x squared, you can describe P by saying that its mean is 7 and the expected value of x squared is 55. You can work that out. I'm not going to do that here. For the second one, the mean is 5.5, and the expected value of x squared turns out to be 38.5. And so you can see that these 2 different distributions have different moments. It's possible to have 2 different distributions that have the same set of moments, but at the very least, we're giving some information about our distribution. So, I think I've been using this word already, but the expected value of a feature is called a moment. And that's all the word moment means, is the expected value of some feature that we picked ahead of time. But there's a specific set of moments that, that turn out to be important, which are the moments for monomials, meaning, x squared, x cubed, and so forth. And so the moment of one of these monomials is called the first, second, third moment, depending on whether it's a first degree, second degree, or third degree, or whatever polynomial. All right, and so we're going to write t in this set of notes for our feature vector. So t of x is in r to the d. It's d real numbers for each possible outcome of x. And t bar is going to be the expected value of t. So t of x is the feature vector and t bar is the moment vector. So here, for example, we could choose x and x squared as our features, and then their expected values become our moments. And you can see t depends on x, and t bar does not, right? Because it's expected over x, right? Like it gets rid of x by taking the expectation over x. All right, so why did I go through features and moments? Basically, it's because we're going to use these features and moments to help us build a model. So first, let's talk about choosing the features, right? So we're going to choose features that help us build a model, meaning that they're going to cover aspects of the distribution that we're not sure of and that might change independently of one another. So for example, if we start by choosing x as a feature, that means that we think it's useful to describe the distribution by its mean. That means we don't know the mean ahead of time, and we think that it gives us some information about the distribution to tell us the mean. If we add then the second moment, e of x squared, that tells us that basically we're saying that even if somebody told us the mean, we still wouldn't know the distribution, and in particular, we still wouldn't know the second moment of the distribution, meaning that we don't know the variance. And then we could add, the indicator function for whether x is less than or equal to 5. And that tells us that even knowing the mean and variance, we're still uncertain about whether x is going to be bigger or smaller than 5. And so each time we add a new feature, what we're doing is we're trying to capture as much additional information as possible about the distribution, given that we know the values of all of the other moments. All right, so we're going to build a model based on this feature vector. And we'd like to use the vector of moments as our parameter that we're going to learn. So what that means is we're going to fix our set of outcomes and we're going to fix our feature function. And then in order to specify a distribution, what we're going to do is we're going to pick t bar, right? We're going to pick the vector of moments. And this is called the mean parameterization of a distribution because t bar is a mean. But in general, there could be a lot of distributions that have the same value of t bar. And so instead of just saying we're going to specify a distribution by picking t bar, we have to say how t bar leads to a distribution. And the way we're going to do that is maximum entropy. So what is maximum entropy? It says that what we should do is to pick the distribution that assumes the least possible about x beyond what's given, namely beyond the vector of moments that we've already specified. And so what that means is that we pick the distribution that has highest entropy among all of the distributions that match the desired moment vector. So we just talked about information and entropy. So if you remember, the definition of entropy was that Alice and Bob both know a distribution, but only Alice knows the value of the random variable. How many bits does Alice have to send Bob? So that's the entropy, the amount of extra information that Alice has. Maxent is the one that maximizes this entropy, right? In other words, says that it's going to make Alice send the longest possible message on average. Why do we want to do that? Well, that's assuming the least possible about the distribution, because it says that we measure how much we've assumed by how many bits are left in the amount of uncertainty that Bob has about the value, right? So if we assume the least possible, then Alice is going to have to send a long message. If we assume more, then Alice can send shorter and shorter messages until we assume so much that Alice doesn't even have to send a message. All right, so a generalization of maximum entropy is minimum relative entropy. And so instead of choosing the maxent distribution, the distribution that maximizes entropy, what we're going to choose is the distribution that minimizes relative entropy to some fixed given distribution P0, which is called the base distribution. So if P0 is uniform, minimizing the relative entropy to P0 is the same as maximizing entropy. We saw in the previous set of notes that when one of the distributions is uniform, then the relative entropy is just a constant away from the entropy. Excuse me. And so instead we're going to pick, if we pick P0 non-uniform, what that does is it lets us favor some values of x over others ahead of time before we're doing the maxent. So for example, we might use it to favor small numbers or states near Pennsylvania or something like that. So why would we want to do this? One good reason is, so if you remember from last mini, we talked about the effect of discretization on probability distributions. And so if you have a continuous random variable, let's say a real number, you could discretize it multiple ways. Let's say you could use a fixed point representation, just chop up the interval from minus 10 to the 8 to plus 10 to the 8 into equal and tiny slices, or you could use a floating point representation like a C float type. Both of those are very reasonable discretizations of a real number, but they have different properties. In particular, floating point representation has much more dense samples near zero, whereas fixed point has an equal density of samples everywhere. And so let's say that you had already fixed on the fixed point representation, but for some particular task, you thought a floating point representation would be more appropriate. Then you could use the base measure, P0, to compensate for the difference in density of discretization. You would basically up the base measure, increase the base measure near zero in order to achieve the same effect as having discretized more finely there. All right, so let's see. So maximum entropy and minimum relative entropy. Sorry. I don't lecture for a week and suddenly my voice is not able to last the full 80 minutes. I apologize for that. All right, so given that we want to use maximum entropy, it makes sense to ask how can we compute the max-end distribution. And so we're going to talk about how to do that. It turns out that there's a lot of fairly heavy math that goes into figuring out how to compute this, and we're not going to go there. I'm just going to give you some definitions and some facts that many smart people have proven that are enough to help us be able to compute the max-end distribution. All right, so the first fact is that the solution to the max-end problem always has this functional form. So the base measure shows up here, the vector of statistics, of features shows up here. There are two new things, theta and g of theta. So theta is just a vector of parameters. We know the functional form, but we don't know theta, and so in order to find a max-end distribution, we have to find theta. And g of theta is just a function that means that the distribution sums to 1. So this form is called an exponential family distribution, and theta is called the natural parameter vector. It's called something different to contrast with the mean parameter vector, which would be just the vector of moments. So in order to go from here to an actual explicit expression, there's two difficulties that we need to resolve. One of them is we got to figure out an expression for g, and the other is that we have to solve for the value of theta that we need to achieve a particular vector of moments. All right, so you can write out an expression for g here. It turns out that that expression makes sense because we know that, right, so we know that sum over x, p theta of x is equal to 1, right? Which means that 1 is equal to the sum over x of, so p theta of x is p0 of x, x of t of x dot theta minus g of theta, right? That's just taking that expression and copying it in, right? That's a minus sign. then we can split apart, right? E to the a plus b is e to the a times e to the b. So we have e to the minus g of theta, and that this e to the minus g of theta doesn't have an x in it, and so we can factor it out. So this is equal to e to the minus g of theta times sum over x, p0 of x, exp of t of x dot theta, right? And then divide through, right? Dividing by e to the minus something is just e to the plus something. So we have e to the g of theta is equal to sum over x, that same expression, p0 of x, exp of t of x dot theta, right? And then if you take the log of both sides here, we get exactly this expression here that I gave for g of theta. So, right, so we can get this expression for g just from the fact that probability distribution sum for 1. This expression is not very convenient, but it turns out that in a lot of useful cases, we can use that expression to solve, we can simplify that expression and get a nice expression for g, and we'll hopefully see some examples later. All right, so once we know a nice expression for g, the second thing we've got to do is figure out what is the value of theta. And we determine theta, like I said, from the requirement that we have to achieve the given vector of moments t bar. And that turns out to be equivalent to g prime of theta equals t bar. So this is a potentially nonlinear equation in theta, and we can solve it to try and find the value of theta. Now, in order for this to make sense, you have to have that, g is differentiable, which it turns out it always is, and that the derivative of g turns out to be an invertible function, which it turns out it always is. So both of those are, deep facts. You shouldn't necessarily be able to figure out how to prove them, but this equation, it turns out is a very useful way to be able to figure out the value of theta given the value of t bar. All right, so that was a very general description of how to solve maximum entropy. It turns out we already saw a very simple example of maxent in an exponential family. It turns out that the Bernoulli family of distributions is maxent, meaning that if we take as our base distribution the uniform distribution over the two outcomes 0 and 1, and we take as our feature vector just the single feature x, then the corresponding moment is the probability of seeing 1, which is what you would expect in a Bernoulli distribution. And if you solve for the maximum entropy distribution, you just get that it is the Bernoulli distribution with a given probability. Maybe a little bit more complicated is Poisson. Okay, we've got some... So we have a question about choosing moments. So the question is, if we choose x as a feature, we're saying that we don't know the mean ahead of time. So if we have x, don't we have e of x? No. So x is a random variable. So when I say we have x, that means that we have the realized value of x, a sample from x. It has some distribution p of x, and if we had p of x, we could compute the mean, but we don't, right? So the idea is that we're getting samples from some distribution, but we don't know that distribution ahead of time. We want to say that there's some family of distributions that it might be, and we want to pin down what distribution it actually is by looking at the samples. Let's see. All right. So we just did Bernoulli as an example. Another example is the Poisson family. So if our feature vector is just the single feature x, and our possible outcomes are the non-negative integers, and we put our base distribution proportional to 1 over x factorial. It turns out that the minimum relative entropy distribution is a Poisson distribution. Not obvious, but if you work it out, it turns out to be true. And a ton of other families that you will have seen turn out to be exponential families of distributions. So Gaussian, chi-square, negative binomial, right? So it's an interesting exercise and one that can sort of help you make sure that you understand the definitions that we've given so far to try and work out how to express a given distribution in the form that we gave above. In other words, how to show that they're exponential families. So for example, if you want to try the exercise, you could go to Wikipedia for the negative binomial distribution and work out how to express it as an exponential family. So maybe even more interesting than the pre-chosen examples that other people have worked out ahead of time is to build our own examples. And the way we build our own examples is by choosing a feature vector. So here's an example that I actually saw in a paper that I read. Let's say we want to build, it's simplified and abstracted from that paper, but let's say we want to build a model of the distribution of a particular type of insect in the area around Pittsburgh, right? And so we take all of the greater Pittsburgh metro area and we divide it up into plots of land. Let's say 1 million plots of land, and we consider every, we send out a whole bunch of field biologists to have them collect samples, and we count how many samples they collect in each one of these plots of land. And so we could, if we wanted to, think of each insect sighting as a sample from a categorical distribution over the plots, right? There are some plots where there's a higher population of insects and therefore more probability of finding one. But if we have 1 million plots, we don't want to learn 999,999 separate probabilities. And so instead, what we could do is assign features to the plots. So features could be things like the average temperature or the average rainfall, or how much higher the average rainfall is in the spring versus the fall. Or is it urban or suburban, or is there a river nearby, right? Like you can imagine all sorts of useful features. Given those features, we would then construct an exponential family of distributions using those features by solving maximum entropy problems. And that would be a reasonable family of distributions to model this insect population. So let's do one more block before we close for today. We talked at the end of last mini about maximum likelihood for fitting a distribution. And then earlier today, we talked about maximum entropy and minimum relative entropy, which are also letting us choose a distribution. And so you might ask, which of these two methods should you use? And it turns out you don't have to decide. It turns out that there are different views of the same process. So in particular, if you're given a base distribution P0 and features T of x, you could construct an exponential family of distributions using that base distribution and those features, and use it to maximize the likelihood of a sequence of observations. Or you could compute the observed mean feature vector T bar, meaning just the average over all of our examples of the feature vector of each of those examples, and then pick the distribution that's minimum relative entropy to P0 given that feature vector, or given that observed mean feature vector. And those will get you the exact same answer. And so you don't have to choose between maximum likelihood and maximum entropy. They are they're getting at a very similar thing. Basically, the main difference is whether you find it more comfortable to assume that you're in an exponential family of distributions and ask for the maximum likelihood, or to assume that what you want is a distribution that matches the given vector of moments and choose the one that has maximum entropy. And my empirical experience is that some few people feel more comfortable with one of those explanations and others feel more comfortable with the other one. But since they get to the same place in the end, you can choose whichever one you like better. All right, so one more question. Somebody wants to know how we know G. And we don't know G ahead of time. We have to compute it, right? So here we have an expression for G that we derived. And this expression is typically too complicated. And so if we want to know a nice expression for G, we have to figure out how to simplify it. And so for each one of the examples, Bernoulli, Poisson negative binomial, somebody's gone out and figured out what that G is, and you can look up on Wikipedia or in the back of your stats textbook what that is, or you can try and derive it yourself for one of those examples to check the to check your calculus or combinatorics skill, or for a new example in order to be able to work with it in a machine learning model. All right, so I think that's enough for today. As always, my office hours start now and go until 3:30. So if you're new, the procedure for office hours is just message me on Hangouts or ask questions on Piazza, or if you prefer, come to my office and ask me questions, and I will do my best to answer all of them until 3:30, and then again later in the evening when I have time after my other meetings. All right, so hope you enjoyed the first class, and I'll see you guys again on Wednesday. Talk to you later.